Hello, my name is Nicole Meyer, and I'm going to be going over how I came up with a proposed structure um, using a given molecular formula and some um, NMR tables and an IR table. So our given molecular formula is C6H12O2, and we can go ahead and use this equation right here to determine our degree of unsaturation. So we're going to just plug in our numbers, our carbons and our hydrogens, and divide it by 2, and that gives us a degree of unsaturation of 1. With that degree of unsaturation, we do know that that indicates a double bond or a ring being present in the structure, and also these oxygens are not going to affect the equation. Looking at our IR and the different peaks that we see here, some of the more notable peaks are going to be here at 1200. This one I'm going to say is a CO single bond. And then in this area between 15 to 1000 is going to be our CC single bonds. Over here, another notable is at 1750. That nice sharp peak looks like a CO double bond, which is very important. And then we have over here, we have between 2800 and 3000 some sp2 CH bonds and sp3 CH bonds, and then just a little bit of fingerprinting down in here. Moving on to our 13C NMR, we have tetrahedral sp3 carbons upfield to the right, and these are going to show up below 80 parts per million. We also have downfield, one peak showing up near 175, and these downfield peaks are going to be our trigonal planar sp2 carbons. So from the numbers that are showing up on here and what we've looked at in our IR, I think this peak at 175 is going to be an ester, because we know we have a CO double bond, and then there was also an O bond, a CO bond in there. And then another thing to kind of look at is the number of peaks, which is kind of hard to tell, but there's either 5 or 6, so you're going to look at these peaks that are here. And this one, I think, has 2 in there, so I'm going to say 6 unique peaks representing 6 symmetrically inequivalent carbons. So these carbons are absorbing at different shifts, and this is going to be important to know at the end when we're looking at a possible structure. And finally, we're looking at our 1H NMR peaks, and the multiplicity is really hard to look at on here, but what is given is our integration. So we can look at all those integrations, and we know we're working with 3 H's, and we're working with 2 H's. So that's this right here. And this is going to relate to the number of protons, as it's called, when you're looking at 1H NMR, or the number of hydrogens present. Like I said, the multiplicity is kind of hard to really count out in here, but from these different chemical shifts and our integration numbers, we can kind of come up with some interpretations here, which you'll see in the chart, which that'll also kind of coordinate with a possible structure that we come up with at the end. So my proposed structure is methylpentanoate, and we went with this structure because it does show 6 carbons, 12 hydrogens, 2 oxygens, the 1 double bond that we were looking for. And the other thing that kind of set this one apart was we know from our degrees of unsaturation that we have a double bond or a ring. Well, we can rule out the ring because with the IR, there was no classic stretch around 1600. And in our 13C NMR, there was no peak at about 150 parts per million, which we would expect to see with a ring. There was one at 175, but that's more like an ester. The other things that made me go with this structure were the 6 unique carbons. So when we look at the symmetry on here, we know that each carbon is different. There's not going to be 2 that are similar. So thank you for listening and have a good day.